Hello, my name is Craig O'Neill, and I'll be talking today about sub-bottom profiling and what it can tell you about the subsurface of the seafloor. So, to start off anyway, sub-bottom profiling is a geophysics technique and it has a lot in common with traditional geophysics techniques such as reflection seismology and also multi-beam sonar, which is effectively a very short wavelength version of what I'll be talking about today. The way in which it works is we tend to create a sound source or an acoustic source either behind a boat. In this case, we've got a boomer plate being towed off the back of that boat, or in these days, we often attach it to the boat itself. Now that creates an acoustic source which travels downwards through the water column and hits the seafloor. Now at that point, some of that energy from that source is bounced back, and we can hear those reflections bouncing back on what's called a hydrophone array, which is pictured here as a streamer hydrophone. And these are effectively very sensitive microphones listening to those sounds coming off the seafloor. And from the time it took for the sound to go down and come back up, we're able to tell exactly how deep the seafloor is at that point. Now, the cool thing about sub-bottom profiling is that some of that signal actually penetrates the seafloor and hits layers underneath the seabed, and it bounces off those layers, continues to the surface, and we can hear those in the hydrophone array as well as later reflections coming back. And that allows us to tell something about what's going on underneath the seafloor in these areas, which is really useful information. It can tell you things about where the bedrock is and the rock contact. It can tell you about the sediment structure, old coral growth beneath existing sediments, all sorts of things. So this is what we're effectively going to be talking about today, and I'm going to run you through a little bit of this lecture, which is going to consist mostly of looking at the basics behind it, the hardware. Then we're going to be looking at what we do in terms of processing the data, and then we're going to be looking at what we actually do in terms of interpreting it. And when you get your data back from a sub-bottom profiling survey, it should look something like this. This is a pretty standard sub-bottom profile data set. This is from a cruise on the Great Barrier Reef, and you'll be working on this data set in the practicals. And you can see, what we're mostly seeing here is the sea surface at the top. We can see the seafloor as a hard reflector there, a little bit of stuff going on underneath that in terms of the sediment structure and also the bedrock contact. But then we can see other interesting things going on, like I've mentioned, multiples down the bottom. And we're going to explain what those are, how to interpret them, and how to extract information from this section as we go on. Now, as I sort of led into at the start, sub-bottom profiling has a lot in common with reflection seismic, so there's a really long literature and long legacy to these sorts of data. Now, in the case of seismics, it can be a bit contentious these days. They often use high energy air guns in seismics that basically create an underwater explosion that creates a really big acoustic source that can go deep into the crust, and it lets oil companies image what's going on kilometers underneath it. The problem with letting off explosions in the ocean is anything that's sensitive to ocean acoustics, and whales are a classic example, can be really affected by these sorts of acquisition surveys. So it's made seismics very contentious in the oceans. Now, sadly, it is the gold standard for subsurface information in the ocean, so it's hard to get around the need for it in a lot of industries, including studies of the oceanic seafloor. Now, what we do to get around it generally is all seismic surveys, by legislation these days, have to have a marine mammal observer on board. And this is someone who basically watches whales for a living. They'll be out on the boat or on the seashore for nearshore surveys, and they will be looking for marine citizen activity, so spouts and things like that. And if they see it within a certain range from a boat, they will shut down that survey or power it down until the citizens move on, and then they can start up again. Now, with sub-bottom profiling, it's not quite the same level of problem because we use way less power in sub-bottom profiling than you would in a reflection seismic survey. But some of the techniques we use are, they're heard by citizens. So a common sense approach goes to the acquisition of these data as well. You don't do it if you've got a pod of dolphins off the starboard side. So what we're going to do in this lecture anyway is look at the hardware so you understand the differences between the different sorts of acoustic sources we use and whether or not they might be a problem. Then we're going to talk a little bit about the physics of what's going on, and this is standard reflection seismology at this point, and you might also think of this section as what a geophysicist is doing to your data before you get to see it. So this is a lot of processing that you won't ever have to do unless you actually go on to become a geophysicist, but it's useful to know what's actually being done to your data before you get a section to interpret. And then the last bit is a very brief introduction to the interpretation of sub-bottom profiling sections. All right, the first part anyway is the toys. So a typical sub-bottom profiling setup is shown in the picture to the left here, where we have a boat, a catamaran in this case, which has a computer on board doing the data acquisition and processing. Now that's hooked up to a few things. The first is a seismic energy source, a continuous seismic profiling, CSP, power source. And this effectively is a big capacitor bank that provides an enormous lot of power to the seismic sources, which are listed there, either a boomer or a sparker source. So these are the high energy sources that we typically use in a survey where we want to see really deep into that crust and rock beneath the sea surface. So both of these, we're effectively sending a big charge down it. In the case, of a sparker, it's a classic cavitation effect. You've got a big voltage drop across a couple of electrodes. It creates a spark. It creates a cavity, basically, an air cavity or plasma cavity in there. That implodes, and that implosion creates a little pop, basically like a bubble popping, but quite loud, which creates your acoustic source, and that penetrates down. So these are serious systems. There's a serious amount of power and voltages involved in this. So there's a lot of health and safety around actually using these properly. But, they're a repeatable system. You're able to just charge them up and continually create these bubbles and get these acoustic signals in. A boomer plate does a similar thing with this plate-like system. And in both of these, you're able to generate very big signals, low frequency, and penetrate into those deeper layers quite well. Now, these things create the source. In the case of this style survey, we need something to listen to the reflections coming back, and that's generally done by a hydrophone array, which is shown up in the top right as well, coiled up. And what this effectively is a bunch of transducers, so the same technology as in your standard microphone, but waterproof here. And they're in a cable, and they listen to those reflections coming back and record them. And each of those transducers gets recorded separately, and the further you are away on that array, the later those reflections will come back. And that allows you to get a spread, an image of what's going on underneath. Now, the other style of techniques we might use are higher frequency chirps and pingers. And if you look on the left-hand side, you'll see a graph showing where sparkers and boomers sit in terms of frequency, and you can see these chirps and pingers, which I'll talk about next, are much higher frequency. So sparkers and boomers, they see different levels in the sediment. So both of them, we're looking at penetrations well over a few hundred meters. So we're seeing quite deep in the seafloor for both of these techniques. They're using quite a lot of power each time. A boomer tends to be really good at seeing down to the bedrock. A sparker tends to be a little better at seeing muddy and gravelly sediments. But they're effectively using similar frequency ranges, 500 to 2,000 hertz for a boomer, and a sparker 100 to 2,000 hertz. They are high power, and so they're good for seeing basement, but they're not good for imaging very fine layers because their frequencies can be quite low. And the other thing, as I mentioned, is these two guys are high energy. They're sort of between, sub-bottom between something like multi-beam sonar energies and air gun energies. So they're pushing up there. The one behind doing a proper reflection seismic with an actual air gun, which is like letting off little air bombs in the ocean, which whales really don't like. So the main thing is you have to be cognizant of marine life in the area as you do these sorts of surveys and the impacts you may be having on them, and work out whether or not you need a marine mammal observer on board during the acquisition stage of these surveys. Now, at the other end, the high frequency end, we have pieces of kit like Chirp, which is shown on the left as that little yellow thing, and a pinger, which is black underneath it. The Chirp tends to be towed behind a boat, and it has an acoustic source, which is quite interesting. It's called a chirp signal where the frequency actually changes through time, and you can see that in the graph at the top. You've got a boomer signal, which is a big explosion basically. You've got the chirp, which is a very controlled frequency increase, and that increase in frequency, if you listen to it, it actually sounds like a bird chirp. We have a pinger next, which is a very clean seismic signal in the orange. And then we have what's called a parametric sweep up the top right, which I'll talk about a little later on. So these have the source and a receiver built into the system. So as you're creating this ping or this chirp signal, it goes down, it reflects straight back up and is heard by a geophone within the system itself. So you're effectively looking straight up and down as you go at what's directly underneath you, and as you sail the ship along, you're able to build up a picture of what's underneath. Now, to give you an idea, pinger normally is between 1 and 10 kilohertz, so on the order of 10 times higher frequency than what a boomer or sparkle would typically do, and a chirp signal can reach frequencies even higher than that. So they're both meant to be targeting certain similar levels within the marine sediments. They're very, very good. I mean, a chirp is very good within the upper few meters of subsurface. It will give you a very good picture of structures within there. They do tend to struggle in coarse material because you get a lot of scattering of those waves, and you don't tend to get as much penetration as a bigger seismic source as well. Now, the way the industry has been moving, you may or may not see this data because not everyone has one yet, are these parametric sweep signals, which generates this low frequency pulse. And it's got basically two pulses interfering to generate the source, but it's very cool. And what it means is you can cover a range of frequencies and penetration with these. And a lot of modern systems are getting the best out of resolving the shallow stuff, but also being able to see deep with these parametric systems. So you'll probably see these coming onto the market more and more in the future. So they're the sort of spread of sources we might use. To give you an idea of what the difference between them is in terms of what you'd see, up the top I've got a chirp profiler, and you can see in that chirp profiler we can see the seafloor topography great. We can see the shallow sediments really, really well defined, the roughness of some of the rocks at the bottom and a bit of the rock profile underneath, but it starts to get fuzzy very quickly. The boomer, on the other hand, down the bottom, picks up that deep stuff really well. We see the rock sediment interface really deep down on the left-hand side quite well. The surface isn't as well defined at all. We don't have that same resolution. And the shallow layers, they're just all blurred together. We're not seeing the differences in them in the fine sediment structure at all. So that's the trade-off really between a low frequency, high power source like a boomer and a very high frequency but lower power source like the chirp. Now, how do we get this data? How do we go from the raw data on a ship to something we can actually interpret? And this is effectively what a geophysicist on board would do to your data before you would see it, perhaps, if you're just interested in the interpretation. So by and large, the mechanics of this come from the field of reflection seismology. And what we're more or less looking at here on the left-hand side is a raw seismic source. So if we had a shot in the middle and we had a hydrophone array spread out on either side of that source, this is what we'd see. Each of those little wiggly lines which go down in time effectively correspond to one hydrophone that's been listening to reflections coming back. And you can see that underneath the surface in the direct arrival, in this case through the water, we see these little parabola-like things. Now these would correspond to individual reflectors underneath. Now they look like parabolas, not because they really are parabolas, but because we've got the hydrophones getting further and further away. And as they're getting further and further away, you could do the trig and you work out basically the distance is increasing as they're squared, which is why these things look like a parabola. So what we're going to talk about is how we get from that raw data on the left to a section like we see on the right, which gives us information like that little top block diagram of what the geology is underneath. So that's the goal. Now, the reason why we get reflections in the first place is because we've got a change in the properties of the sedimentary layer, and the particular properties we're interested in is what's called acoustic impedance. Now, this is a product of the velocity times the density of a material. So we could have a change in the velocity of the material or a change in the density of two layers on top of each other, and that would give us the difference in acoustic impedance. Now, the bigger that difference, the bigger the reflected signal is going to be. As you can see, sort of on that left-hand side, that little wiggle diagram, as the signal's coming down, bits are getting reflected off the interface, and the strength of that reflection depends on the strength of the difference between these two materials. So you can imagine something like water and sediment has quite a strong acoustic impedance contrast, and it gives us a strong signal, whereas a silt on another silt probably doesn't have the same contrast, so we're not going to get as well developed a signal. Now, in a typical reflection survey, we do a number of shots at different points, and this goes for land or for marine surveys, and we take all that information together and combine them together to try and get a picture of what's going on underneath. So the applications of this, I mean, obviously a lot of this comes out of petroleum and mineral exploration, and this is why the field has been so well developed, because, let's face it, petrol companies have put a lot of money into this over many years. But it is, it's good for base and structure in general. So for a lot of projects, CO2 sequestration, green hydrogen storage, and even major infrastructure projects like offshore wind farms, this is a really, really critical piece of information. It's really useful for understanding Earth's structure, the nature of plate tectonic margins, structure of continents, etc., etc., and also in the geotechnical and environmental systems. If you're going to put in any big infrastructure, you generally do some type of survey, and in the marine offshore environment, these sorts of sub-bottom profiling surveys are bread and butter if you're putting in a desalination plant or laying out a pipeline, and I've been involved in a few of those works. You absolutely need detailed sub-bottom profiling information over the entire area so you can make informed decisions about how to engineer a structure. So let's talk about what we actually get in terms of reflections to start with. Now, as I mentioned, incident wave, this is your source, comes in and it meets a reflector. This could be the seafloor. And part of that wave will get reflected straight back with an amplitude A. And part of that wave will get transmitted through. So you're losing a bit of energy in the reflected wave, and then some of the energy is going in transmitted wave. So you're immediately sort of splitting your incoming energy and amplitude of the wave. Some's bouncing off and some's traveling through. Now, I literally swear this is the last equation slide, but the way in which we determine how much is reflected and how much is transmitted comes down to the acoustic impedance, which I mentioned, which is velocity times density. Now, the reflection coefficient determines exactly how much the reflected amplitude, A1, divided by the incoming amplitude, A0. The reflection basically is determined by the ratio of those two. And you can work it out in terms of impedances by that equation there, Z2 minus Z1, Z2 plus over Z2 plus Z1. Now that determines uniquely exactly how much energy is reflected. So if you've got a big contrast between Z2 and Z1, you'll get a very strong reflection. The transmission is going to be the sort of corollary of that. So how much energy goes through, it's going to be 2 to Z1 on Z2 plus Z1. And that determines how much energy will pass through the interface and continue down to give you deeper reflections. If you wanted to understand it in terms of energy, the relationships are given to the right-hand side. It's just the squared of those. But effectively, this describes how strong your reflections are going to be in seismology. The bigger the contrast between Z2 and Z1, the stronger your reflection is going to be. Right, so if we now look, you can actually work this out. If you knew the density and velocities of each one, if we start from the left-hand side, we have a shot going down through layer 1, that may be the seawater. Part of it gets reflected off, and that's R12 in that diagram. Part of it gets transmitted. And if we look at the right-hand side diagram, you can see how it sort of builds up. We've got the source, part gets reflected, part gets transmitted, that's T1, 2. And then it comes down and hits the next interface, and part goes down, which is the deepest one in layer 3, and part of it gets reflected back up. Now that wave that's getting reflected back up hits the first interface again, and again, part gets transmitted through the first interface, and part gets reflected back down. So you can see there's a lot of reflections and internal bouncing around going on before that signal arrives back at the surface and is detected by a geophone or a hydrophone. But that's essentially the way the wave is working, and at each of those interfaces you're losing a little bit more energy. Now, this is showing just again for an incident wave in a layered media what the little wiggles coming back might look like in your seismogram. So we've got the wave coming down, it's hitting an acoustic impedance contrast. We can work out what that reflection coefficient is if we know what the rocks are. We know their velocities and densities, and that's plotted in that little bar diagram in the third column. Now, in terms of the waves, you can see some are coming down and then bouncing back up. And if we're listening at the surface to those upcoming waves, they'd all add together and give us basically this little wiggly diagram here, where each of those wiggles corresponds to a reflection in the original waveform coming back up. So that energy decays through time because the deeper down those reflections are, the more energy we've lost before we've reached that interface. The other thing to note too, the stronger the reflection coefficient, the stronger the signal of the reflection that we get in the seismogram. But if we get negative acoustic impedances, like the velocity slower in one layer compared to the one above, the signal can actually flip. Instead of getting a rarefaction first, we could get a compression first, or vice versa. And so that polarity, whether the wiggle goes up or down compared to the original signal, can actually tell you a lot about what the properties of those rocks or sediments are underneath. So there's a lot of information in that seismogram, some of which we use when you get into advanced seismic interpretation, but it's worth just pointing out now that there's an enormous amount you can pull from the information you get from this sort of seismogram. Now let's go from those raw shot records to a seismic section. What are the steps? So a typical seismic shot, as we mentioned, looks like what we've got on the left. That'll be a shot in the middle and geophones spread out on either side. That direct wave there in red basically is the wave that's coming directly from your shot to the hydrophones, probably directly through the water layer, so it's the path of least distance really. At some point we've got a reflection hyperbola there. You can see in the lighter green that corresponds to a reflector. It's probably flat and it's just curving because as you get further away the distance increases as t squared basically, or x squared. Right in the middle there, you see these big wobbly things. These are basically surface waves, or what we call ground roll in reflection seismology, because they're not interested in this information. But you know, these are high frequency waves that are traveling along an interface quite slowly. We don't get them as much in marine data as we do in terrestrial data, but it's worth pointing out that really high amplitude surface waves can travel along the seafloor as well. So the relationship between the distance away of a geophone and the time it takes for it to get back is shown by that equation there. So effectively it's t0 equals 2 times the depth z over the velocity, more or less. Now the steps we do for processing it, we gather together all the common shots, like we've just seen one previously. We rearrange all the traces to get it at a common midpoint, and then, well, this is going to be clearer when I actually show the steps. We apply what's called a normal move out, and we combine the stacked traces, and then we give it to a geologist to interpret. So the step one, anyway, if we had, for instance, a boat going along and it has a shot and a geophone array coming out the back, we'd get something like what's shown in that bottom left figure, where we have a shot up near the surface, and the hydrophones that are further away record arrivals coming deeper and deeper. So that's step one. We gather all those together, and that's called common shot data. Right, so we get to step two, and what we effectively do is say, right, well, for this position here, from all our shots, we've actually got a lot of information around it. So let's rearrange all the shots so that we have everything at this particular point at a central position, a common midpoint, and all the other shots that were close to it, that are recording something at a distance close to it, let's stack them all up. And this is called a common midpoint stack. It gathers and reorders all the shot traces around common subsurface points. And so now we're getting like that original seismogram that I showed you previously. It's like the shot was in the middle and we're listening to everything come around either side of it. And you can see those initial surface arrivals, direct wave arrivals, and you can see the reflection information deeper down underneath that. Now, number of traces around a common midpoint is equal to, it's what we've called in seismics the fold of the survey. If you ever hear that term, that's not very relevant to us today, but it's effectively like having a shot in the middle and hydrophone arrays off either side listening to it. What do we do with that? The next step is getting rid of that curve that we see in those reflectors, because that's not real. That's just an effect of the hydrophones being further away from the shot point. But we know the relationship to it. We've got this parabolic relationship, which is shown by that equation to the right-hand side. But effectively what we're doing is if we know the velocity, we've got a velocity model, we can fit where that parabola is curving down, and then we can remove that parabolic effect and flatten it out, which is what's shown at the bottom. We take that time delay due to the distance being further, and we subtract that from each trace, and we flatten out the traces, as you can see in the bottom right. Now, the last thing is, if we've got a lot of traces at the same point, we stack them together. So basically, we're averaging them all together. And the reason for that is the real signal will be real signal in each trace, so it will add together. The bits of noise, which are just kind of random noise in the traces, they'll tend to cancel out, and so we'll get rid of them. So by stacking traces, adding them together like that, we increase the signal, at the same time we decrease the noise. So this is pretty classic geophysics. You generally take quite a few stacks in order to improve your information. And this is the process. Basically, we go through this and we do this for all the shots, or all the common midpoint shots, and we go through and we add them all up into a seismogram, which eventually would look something like this. So the end result of what we get from that processing is a seismic section. This is generally the point at which the on-ship geophysicist, if that's not you, would give you this section to then interpret against what you know is going on in the seafloor, either dredge samples or grabs, or if you're really lucky, some drill core data as well. But you can see some really strong reflectors there. They probably correspond to big contrast in the properties between the sediments or rocks underneath. And yeah, so this is the basic information that we'd be looking at. All right, last off, I wanted to show you about a little bit about interpreting typical sub-bottom profiling sections that we'd get in marine environments, and particularly in this case, the Great Barrier Reef. So this is off a cruise, which Luke can tell you more about, but effectively this is real data. Now, I've imported this into ParaView in this case because that's what we're going to be using in class, but it's just to show you some features that we can see in this data set here. Now, at the very top, we've got the sea surface, so everything's referenced relative to that. And if you look very hard, within the water column itself, there are little reflectors and structures there, and they're basically water column reflectors, inversions in the density of the water column, or reflections coming off the boat, which are pretty consistent through time. You can ignore most of these. They're not really of interest. Well, they're probably of interest to, oceanographers or something, but not for us here. The main thing is you get a really hard red line about, a third of the way down there, which is labeled the seafloor. So that's obviously a big reflection contrast between the salt water above and the sediments underneath, and that shows up very, very well, and the sub-bottom profiling has obviously picked that up. Now, before we get into the actual information, I just wanted to show you something else called the multiple. You can see that sitting right down the bottom. I've got a label on a surface called a multiple. That's not actually a real geological feature. What that is, if you can imagine that the seismic source from our pinger or whatever started at the sea surface, it went down to the seafloor, bounced off that and came back up. And that's our seafloor reflector. Now imagine that signal then hit the sea surface and actually bounced off the water-air interface and went back down, hit the seafloor, and then came back up again. So it's traversed the water column 2 times, down, and up. That's a multiple. We would see that in a hydrophone array. Now, we'd basically see it at twice the depth of the seafloor because it's traversed the water column 4 times effectively, twice times 2. And we would actually exaggerate those seafloor features a little bit. So whereas our initial seafloor looks flatter, when it's traversed it down, up, and then down, up again, it exaggerates some of the structure in it. So if you actually see something like this, it's almost exactly twice where the seafloor is, and the structure looks the same, maybe a little exaggerated. And if you actually look underneath it, I can see this hard reflector I've labeled underneath the seafloor, repeated as another hard reflector underneath. We're actually repeating structures within that upper reflection profile as well. So this is all artificial. This is very hard to remove from seismic information, but effectively it's just an artifact of the signal going down, coming up, and then going down and coming up again. So it's just worthwhile pointing it out. It's something you'll have to look at and filter in your brain and get rid of it, because it's a very difficult thing to filter in the data without actually starting to remove real information that's in there as well. Now, if we look at the real information sort of in that middle section under the seafloor, you can see some fairly well-developed sediment reflectors, and in the data you look at, they will be variably present in different places. Here they're okay in the top few meters. And then underneath that, you can see what I've labeled a hard reflector. Now that's pretty consistent with a strong contrast, perhaps between sediment and the bedrock. So normally that would be a bedrock contact. Here in the Great Barrier Reef, that's often associated with a Pleistocene surface where consolidated material, which was pre-Pleistocene, was exposed during marine regression at that time, and then the transgression came and covered up with more sediment, but that's quite a distinct interface in a lot of the sections in this particular area. So keep your eye out for that. That's really the meat and potatoes of the sub-bottom profiling interpretation, in regions like this, is really being able to pick up that sort of hard reflector that may correspond to the bedrock or consolidated material underneath the softer marine sediments above. Now, I won't overinterpret this anymore at this point. It's not actually terribly much going on in this section, but this is a standard example of the sort of data you get. Sometimes it's interesting, sometimes it's not, but this is the basic start of interpretation for you guys, the things to look out for from the geophysics point of view. The rest is really then up to putting this in an environment where you can start interpreting the geology, and that's what we'll be doing in the practical today. All right, that's the end of this little introductory lecture. Craig O'Neill signing out.